Okay, then we can move on to the next question that I hear. And we also found that alpha was L times L plus 1. This means for a particular maximum value of m, we only get one eigenvalue of j squared. Is that correct? Okay, so the idea is something like this. So j squared, if you express it in j plus j minus, that's the most easy way of doing it. J squared, which is say j1 squared plus j2 squared plus j3 squared. These guys, j squared commutes with all the j's, right? So this is something I told you to show by yourself. Has anyone shown it?
Yes, without using the L5V2 beta ones, I showed in 3 of the particular cases.
Okay, that's fine. Yeah. Um, so what does this mean? This means that all the states that we can create in this vector space by applying j plus, j minus, and j3, they will all have the same j squared eigenvalue. Okay? They will not have any other j squared eigenvalue. If you start with some state with some particular value of j3 and you apply these things, you will never be able to change this eigenvalue, right? Is that clear?
I guess that's what the alpha equals L times L plus 1 equation says, does it?
Exactly. So
Okay.
all the states have the same value of alpha. It is L times L plus 1. And we show that, the j squared eigenvalue acting on some state, which we usually label with L instead of L because it's easier, it's going to give you L plus 1. And if I just introduce the value of h bar again, it'll be h bar squared L m, okay? So this is the j squared eigenvalue. So all the states that we create by applying j plus, j minus on these states, they will all have the same j squared eigenvalue. So we can think of our Hilbert space as having a label L. But inside the Hilbert space, there are all these states with different values of m. M equals to, say, plus L, L minus 1, dot, 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 minus L. And all these states are related by, J plus and J minus, okay? And so the L is labeling the whole Hilbert space, whereas the value of J3 is labeling the linearly independent basis vectors in that Hilbert space, the individual vectors. Okay, that's the picture we want. It's a bit like this. Like, suppose you're going to a building, to an office. So the office, you have some, a block of flats. So this is the block of flats. Okay. And this block of flats has some address. And that address is the j squared. But, as you go up and down the floors, you have m is the number of floors, and j plus and j minus are your elevators. Okay. And but the city designers are so clever that they have arranged all the all the buildings in such a way that the height of the building depends on its location, such that this building, the highest floor has the label L, and the lowest floor has the label minus L. So if I give you just the number L, you can tell the location of your block of flats as well as its height, because its height is going to be 2L plus 1. So it's kind of a stupid analogy that I just came up with right now, but that's what I mean, is that this is some Hilbert space. It is completely labeled by L, and the M's are labeling the floors. Okay. Does that make it a bit clearer?
Yeah, the analogy was really nice.
Okay, good. All right, so let me then go back and kind of give a bit of a recap of the last class, and then from there we can. So there'll be a few more angular momentum lectures. Okay, this is a very important topic, and it's not easy. It's technically a little bit involved, not very much involved, but it's conceptually quite subtle. Okay, so please interrupt me.
I actually had a couple of questions.
Yes, you're a bit quiet. Can you speak a bit louder? Can you hear the microphone?
Can you hear me now?
Yeah.
Okay, so every time J minus or J plus acts on the ket alpha L, so S changes. Is there a specific number by which it changes, like 1 or 2 or anything?
So S counts the number of times J minus or J plus acts on it.
Right.
Okay. So that's why S is a positive integer, because it is just a counting it's just counting.
Oh.
But I actually skipped over a step in the last class. I don't know if you guys noticed, because I gave you the expression for the coefficients in terms of L and S's.
Yeah, I was also thinking about that.
Right. So you're supposed to work out from those expression, these expressions, these guys. The coefficient where it's in terms of L and M, you should work that out yourself. Okay, I only wrote those, but I did not give a derivation of how you. So it's very easy. It's just a substitution, but you should think about it. Okay.
Yeah. Okay. Also, at what point does the ladder terminate? Like, it's written that the ladder must terminate at some point, but is there a specific point that we know of?
Yes, we do, and that is given by the value of L.
Oh, so like when it reaches the value of L, or 2L plus 1, is it?
When M is L, that is the highest rung of the ladder.
Okay.
And when M is minus L, that is the lowest rung of the ladder. And what happens is that you go up the ladder by applying J plus, and you go down the ladder at J minus. So if you apply J plus again, you get 0. And if you apply J minus to M, you get 0. Okay.
Okay.
So this ladder has 2L plus 1, rungs. Okay.
Yeah. Okay.
Any more questions?
No, I was just had some confusion and stuff, but it's all right.
Okay. Yeah. I mean, this is confusing. It took me a couple of times, more than a couple of times, to learn this stuff. And even then, I read up. So there's a book I've been using that is really, really nice. It's on the list, and it's a book by what's his name? By just one second. Yeah, so it's a book by Skinner and Binney, and it's my new favorite book on quantum mechanics. Okay.